Okay, having learned the multilayer perceptron and the details of the backpropagation algorithm and some of the technicalities associated with the Jacobians and the Hessians, let us discuss an important architecture which is the convolution neural network. This is one of the basic engines in deep learning algorithms. So, what is the motivation to convolution neural networks? This is neurobiologically motivated, and the structural layout of the multilayer perceptron algorithm has to be devised in accordance to pre-processing steps that are neurobiologically inspired. So, we start with the work of Hubel and Wiesel related to the visual cortex of the cat. From their findings, there are specialized neurons called simple cells and complex cells. The simple cells are locally sensitive, whereas the complex cells, they are complex because they can sense orientation, etc., which are more advanced features. Now, if you have simple cells that can do local operations and you have complex cells that take care of orientation, etc., can we build a neural network that sort of in a way mimics this neurobiological functionality? That is our motivation. With this in mind, we start with the goal. The goal would be to design a multilayer perceptron to recognize 2D/3D shapes and objects with high invariance to translation, rotation, scaling, and some of these affine features, right. And this was very successfully done by LeCun and others who pioneered this idea behind convolution neural networks, and we will study this concept in the next set of slides. So, the first step is the feature extraction part. Each neuron takes its inputs from local receptive fields in the previous layers, forcing to extract the local features. So, what it means is I have a mask that goes across an image or a 1D signal, or it could be a voxel for example, and in the process I extract the local features, and once these features are extracted, the exact location of the feature is less important as long as the relative position with respect to the other features is preserved. So, this is very important that we preserve the relative position with respect to the other features. So, once we do the feature extraction, we do the feature mapping. So, let us see how this is done. So, each computational layer is composed of multiple feature maps, with each feature map being in the form of an appropriate geometry to the signal. For example, it can be a plane for images, or it can be a small 1D array, etc., and they are constrained to share the same synaptic weights. Well, there are two things that happen with this. One is shift invariance. Because we are forcing the feature maps through the convolution operation with the kernel of a smaller size to have shift invariance property, right. If you think about the convolution operation, it has this shift invariance folded in. So, therefore, this property is naturally incorporated by virtue of design. Second, we also have reduction in the number of free parameters, and this can be ensured through weight sharing, right. I can share the same weight across these connections, and therefore, I have reduction in the number of free parameters. It is not a fully connected network where the weights are not shared. The next step would be the subsampling process. Each convolution layer which is already endowed with this shift invariance property, performs some local operations. What I mean with local operations are filtering operations, right, and these filtering operations are followed by nonlinear activation through some nonlinear activation function phi, and then it is followed by subsampling. Because of subsampling, there is reduction in the resolution of the signal. Okay, we will see this when we go through the example as to how the resolution gets reduced. Because of these operations, there is tolerance to the sensitivity of the feature maps with respect to shifts and distortions. Okay, let us see how this architecture works. Right, suppose I have a 26 by 26 input image or an array, it is an array of size 26 by 26. Let us imagine I have 4 masks of size 3 by 3, right. Using these feature masks, I can extract features. In this case I have 4 masks, so I have 4 features, 4 feature maps that I can extract, and they would be of size 24 by 24, right. You can just see this operation 24 plus 3 minus 1 is 26, that is sort of following your convolution idea, right. And there is this nonlinear function phi that is built in to the feature map, right. After I compute the convolution output, I pass it through the nonlinear activation which acts on every element of this array, right, and I have this value that I get. So, the value of the feature map, the value of every point within the feature map has to be viewed through the nonlinear activation function. Post the operation of convolution and nonlinear activation, we subsample, because we have a lot of these feature maps and we have a huge size in the set of feature elements that we can get. We have to downsample this data to avoid the computational burden. Suppose we do subsampling over a 2 by 2 local field, then assuming that we had 4 feature maps, we land up with again 4 feature maps, and each of these maps are of size 12 by 12, and this goes on recursively sort of in a pyramidal fashion, leading to convolution followed by subsampling, convolution followed by subsampling, so on. At this stage you may be wondering, how do I choose this mask? Am I going to have this fixed, or would I let this towards adaptation? This is very important. If you refer to Hekin's book, he mentions about these feature maps and sort of interprets these as filters. I will discuss both of these ideas, one which is non-adaptive, the other which is adaptive, so that you can understand and appreciate the flow of the ideas within both these architectures. Now, we have seen that through this pyramidal cascading effect we have convolution followed by subsampling and so on and so forth. And this idea of convolution followed by subsampling is neurobiologically inspired, because as I mentioned in the very beginning of this lecture, that we want to construct a neural network architecture that is inspired by the original work of Hubel and Wiesel, that characterized simple cells and complex cells. Simple cells that are able to receive local information or can detect local features, and these complex cells that look into more special features such as orientation, etc. Right, and this is the kind of architecture that we have in mind. And as the number of subsampling layers increase, that means I am going down the hierarchy from convolution, subsampling, so on in this cascaded manner, the spatial resolution sort of falls down, which means if I am looking at the spatial resolution of a layer deep down through this convolution followed by subsampling, this spatial resolution is less compared to what I had in the previous layer. This makes sense because suppose I have an image to start with, and I initially extracted features that were local. So, I am just going to mark these, I am just going to mark these with these red dots. So, initially I had these here. As I am doing downsampling, I choose one out of these samples and I may have just a dot here followed by the rest, right. And this idea behind reducing the complexity of the dimension of the feature set that can be accomplished through subsampling lends itself to a reduced resolution in space, right. I have reduced spatial resolution because I am subsampling. Now, let us see how this works through computations, and we will see through an example. Suppose I am given an image like this. This is a 3 by 4 image. This can be treated as an array of integers. If you are doing an 8-bit representation or a 16-bit representation or whatever is your representation, you convert this into, once you sense from the camera, you convert this into a set of integers to the level of bit precision that you want, and that is how your image is represented. Now, we filter the image. At this stage we have a sort of distinction, is this an adaptive filter or a non-adaptive filter, right. So, accordingly you can have two different architectures. So, let us consider a simplistic case where we have a non-adaptive filter, and then I will talk about the adaptation, right. Suppose we filter the image through a mask. Let us imagine that we know the mask already, right. What is the role of the mask? The mask can extract features that are low pass in nature. That means the signal may have content in the low pass region. So, the mask can extract this information. Similarly, it can have information on edges, etc., that are essentially high pass in nature, and the mask can extract those features. A good example to visualize the low pass and high pass filters could be through these two images that I have, A and B. A is more like an almost a circle with which is shaded blue here. This is more low pass content, and if you think about this star shape here with rough edges, this is high pass information because it is edgy, right. Now, what do we think of when we imagine these masks? Let us imagine a 2 by 2 mask, right. This is essentially low pass, it has all ones, it is doing an averaging operation. So, I take this mask and slide this over an image, I have a low pass operation. Similarly, I can have band pass operations by controlling what ones have to be flipped to zeros, so on, to what I can have to be a true high pass mask, right. I take the mask and I apply this on to this integer array, which is my image. So, when I slide this mask through the image in an overlapping manner, that is, I have one block of pixels, one column of pixels that overlap. So, let us imagine I have a 3 by 4 array and I have a 2 by 2 mask, right. This is a mask filter, and I slide this on this 3 by 4 grid, I get a 2 by 3 array at the output, right. You can see and you can sense this. So, this is the first block, this is the second block, this is the third block with a slide of one column of pixels. Similarly, I go to the next row and I have 3 more blocks. So, I have a 2 by 3 array at the output, right. How do these operations work? Let us imagine that I have a mask having values 1 1 1 1, this is all low pass. I convolve with this array which has numbers 1 till 12. The first block is 1 2 5 and 6, right. I take this and convolve, I take a dot product with this mask. So, I land up with 14. Similarly, if I take 2, 3, 6 and 7 and I take the dot product with this mask, then I land up with 13 plus 5, which is 18, and so on and so forth, right. So, this is assuming a fixed set of coefficients for this mask, but bear in mind, in an actual convolution network endowed with adaptation, these coefficients have to be learnt through learning. So, I do not know if it is going to be 1 1 1 1, there can be, these are variables that could be some wi's, and I have to learn the parameters of this mask through learning. Okay. Now, once the features are extracted, we feed this to a nonlinear activation function which acts on each and every point within the array. One such activation function is the rectified linear unit. In the previous discussions, particularly when we derived the backpropagation algorithm, we learned 2 different activation functions. They were the sigmoid activation function, the tan hyperbolic activation function, right. The problem with some of these activation functions that we learned earlier, the sigmoid etc., is that they suffer from the vanishing gradient problem. What is this vanishing gradient problem, right. If I have to compute the local gradient, I have to compute the partial derivatives, right. If I say have 4 partial derivatives and each of the partial derivatives are small, let us say I have to compute 4 partial derivatives and each partial derivative is 0.5. So, it is 0.5 times 0.5 times 0.5 times 0.5 4 times, it is a small value, and if I have more such layers, the number of such diminishing values would be very very large, and that is the vanishing gradient problem. My gradients would vanish, and this again has a detrimental effect in the learning algorithm. So, to prevent this, we have the rectified linear unit. The rectified linear unit does this operation. It is max of 0 comma x. So, rectified linear unit acting on the input x gives max of 0 comma x. That means all negative values are limited to 0 and anything positive is kept at x. The advantage with that is when you take the derivative, of course, you may wonder at 0 what happens. At 0 it is not defined, the derivative does not exist. So, you can treat this as 0 or whatever, and at those points where the derivative is defined, we have a value 1. So, when I compute all these partial derivatives, I no longer have this problem of local gradients which shrink to 0. right. This is a very important advantage, and that is the reason why people use the rectified linear units. Now, how does pooling or subsampling work? So, let us imagine we have a rectified feature map. I mean, post rectification we have a feature map that has the following integers. I have 1, 3, 10, 1 in the first row, 4, 9, 6, 8 in the second row, so on and so forth. I can do max pooling over a 2 by 2 sub block that is non overlapping. So, you may question again here, why should it be non overlapping? Since I already considered masks that overlap or slide across the input array, I do not have to do overlapping at this stage, right, and also it saves me to throw away certain samples which I really do not need. So, with these two practical constraints in mind, we can think of non overlapping max pooling blocks. So, once we do this, let us see how this operation happens. Let us consider this first 2 by 2 sub block of this 4 by 4 array. So, if we consider the array 1, 3, 4, 9, this is the first 2 by 2 sub block. This gives us 9. When we take the max of this array, this gives us 9. I populate it here. Similarly, I take the second sub block of size 2 by 2. This gives me a value 10, and I do this over the rest of the sub blocks, and I get a subsampled image. And we can reiterate these steps from 2 to 4, that is the convolution followed by the subsampling in a pyramidal manner to get a final size as desired, right. So, you may wonder at this stage to what resolution can I go. The resolution depends upon the accuracy that you need and the computation that you can tolerate, right. This is the key idea, and I do this and I raster the 2 by 2 final array. Let us assume that this is my final array. I raster it, I get a feature vector, right. This is in R4. In this example, okay. Now, this feature vector is fed, can be fed. So, I mentioned about two variations. One, have fixed masks over which I can extract the feature maps, and I can land up with a feature vector that I can feed this to the multilayer perceptron with a certain desired response, and I can learn the input output mappings. The other algorithm or the other approach which is commonly followed is to have these masks that are adaptive. So, if I have a feature map, I can have variables like W11, W12, W13, W14 that are unknown, and I have to learn these weights adaptively using the backpropagation algorithm within this context of the convolution network architecture, and finally land up with a feature map that is learned through these associations adaptively, and that is the idea behind the convolution neural networks that we see as a common recipe in deep learning algorithms literature, right. So, you can adopt both the algorithms. If you want, you can have fixed set of masks. These are like our subband filters, and from which we can extract the information. You do this convolution followed by subsampling, land up with a fixed feature vector and then feed this to the network. Instead, I do not know what the mask is. The mask is adaptive and it is parameterized by these weight parameters, and these weight parameters are learnt through the back propagation algorithm through the online through the gradient descent approach in an online manner or batch manner. Okay. And you may also question at this stage, can I bring in any regularity conditions on these adaptive masks, right. You may want to have more than one such mask to be able to have better control to the kind of features that you want to extract. You may put certain conditions on the coefficients of these weight vectors, right. I can have conditions on the elements within the mask, and this can lead to regularized network for learning the input output mappings. Okay, with this we shall stop this lecture on convolutional neural networks. You may wonder if there is a recipe for doing this. You have learnt all the basic features, right. You have learned the derivation of the backpropagation algorithm, you know how the delta rule works for weight adaptation. All we want is to introduce a pre-processing step, which is essentially convolution followed by subsampling and rectification etc. through this pyramidal effect, and that leads us to this architecture. And adaptation and computing the learning rule for the weight to the computing the learning rule for these weights can be done in a very similar manner to what we have done in the derivation of the backpropagation algorithm. So, with this we conclude this lecture, and this will be followed by demonstrations on this algorithm.